Hi, welcome to LGSVL Simulator, a high-fidelity simulator for autonomous driving. My name is Steve Lemke, and I'm a principal engineer and technical evangelist with the Advanced Automotive Platform team at LG Electronics. I've spent the past 2 decades working on system software platforms and developer tools for Palm OS and WebOS at Palm, HP, and LG. I helped prepare and release WebOS to open source, first at HP and later at LG, and have since shifted my attention to innovation projects at LG related to automotive infotainment and autonomous simulation. My team is part of LG's America R&D Lab, or ARL, and our office is located in Santa Clara, California. ARL was previously known as LG's Silicon Valley Lab, which is the SVL in LGSVL, as in the LGSVL simulator. We've been working on LGSVL Simulator for several years now as an open source project at lgsvlsimulator.com and on GitHub. Our mission is to provide an open simulation platform for the development and testing of autonomous driving and future mobility services, and it is our desire to collaborate with industry and academia to create a full-featured and professional, yet accessible and extensible simulation platform, so we can all achieve our individual business or research goals while reducing overall development time as well as cost. In this presentation, I will go over the features and capabilities of LGSVL Simulator and show you several examples of what Unity 3D has enabled us to create so that you can in turn build and test the intelligent, connected, and autonomous vehicles of the future, or the technology that enables them. To start off, you might ask, why should we use simulation to test autonomous vehicles? It's been said that before you can prove that autonomous vehicles are safe, we must first test them by driving billions of miles. As you might imagine, doing that in a fleet of 100 test vehicles, driven 24 hours a day, would take hundreds of years to complete. But we can drive many of these miles in simulation by running thousands of simulations in parallel in the cloud, without risking any lives or accidents in the real world, and we can do that at a fraction of the cost of real-world testing. Every time a developer changes something, whether code in an algorithm or retraining a neural network, those changes can be quickly regression tested in a continuous integration workflow to ensure they don't introduce new bugs or reintroduce any old ones. Simulation can provide coverage testing that is not practical or maybe even possible in the real world, because everything in simulation can be precisely controlled, including the weather, the time of day, and road and traffic conditions. And simulation can also be used to generate synthetic data for machine learning, which is automatically and perfectly labeled. How does a simulator work with an autonomous driving, or AD, software stack? Instead of testing in a real vehicle in the real world, the simulator provides a substitute for the autonomous, or ego vehicle, in a virtual environment that includes roads, traffic lights, vehicles, and pedestrians. We call these NPCs, or non-player characters. It also simulates all of the sensors on the vehicle, including cameras, radar, Lidar, GPS, IMU, and more. The AD stack uses that sensor data for localization and perception. Where is it and what does it see? And then performs prediction and planning to route the vehicle to the desired destination while observing traffic rules and avoiding NPCs. The control module sends acceleration, braking, and steering commands to the simulator, which it then uses to move the ego vehicle within the simulation. LGSVL Simulator is built with Unity 3D and renders photorealistic environments with Unity's high-definition rendering pipeline. It features GPU-accelerated sensor simulation, renders 2D and 3D ground truth, as well as semantic and instance segmentation. AD stacks like Apollo and Autoware connect via ROS or CyberRT bridge to receive and process the data from all of those sensors. New vehicles and environments can be imported or created in Unity, and we've built some powerful tools for creating and annotating, as well as importing and exporting the HD maps that you will need in a variety of formats. There's also an extensive Python API and plenty of sample scripts to externally control simulation and automate your millions or billions of miles of testing. This is all part of the free and fully functional community version of LGSVL Simulator, and we've shared the source code for it on GitHub, so you can build on what we've done and modify or extend it to fit your own needs. While we plan to continue to share this professional quality simulator with our growing community, we're also looking to make this into a viable and sustainable project for LG. To do that, we've been working on some new premium features like distributed simulation, digital twin environment generation, visual scenario editor, and cloud simulation. I'll share a preview of some of those features later in this presentation. As I mentioned earlier, we chose Unity 3D as the graphics engine to power LGSVL Simulator, and when Unity released their high-definition rendering pipeline, or HDRP, we made the decision to adopt it in our simulator, and in order to give our users photorealistic visual imagery by taking advantage of HDRP's physically based lighting and materials and compute shader technology, which takes full advantage of available GPU hardware. You can fully control the environmental settings in our beautifully rendered digital twin environments, including weather and time of day, which allows us to position the sun correctly in the sky based on the specified time. All of these settings can be interactively controlled at runtime or programmatically through our Python API. What you're seeing here is a preview of a recent investigation where we enabled real-time ray tracing to see the resulting improvements in reflections and global illumination. And as I mentioned, you can interactively change all of these parameters. LGSVL Simulator includes several built-in and configurable sensors for autonomous driving, including camera, Lidar, radar, GPS, and IMU. In addition to built-in physical sensors, there are also several virtual sensors. Here you can see segmentation and depth camera visualizations. Instance segmentation is also available, where different instances of an object type can be colored with different shades of the color associated with that object type, such as cars or pedestrians. There are also 2D and 3D ground truth sensors, which can visualize bounding boxes for objects in a scene, as well as publish that information over the sensor bridge. Here you can see sensor visualization of our Lidar and radar sensors, as well as some of our virtual sensors. Our standard built-in rotating Lidar sensor supports 16, 32, 64, and even 128 beams, publishing Lidar point cloud data over the sensor bridge. Although many of our sensors are configurable, it's also possible to make your own sensors. Because LGSVL Simulator is open source, you've always been able to download the source code and modify it or extend our built-in sensors or create entirely new ones. Even sensors which do not yet, or perhaps could not, exist in the real world. These sensors can access, sample, and publish low-level or raw or high-level object data from within the scene of the simulated environment, including the entire ground truth. Because we create, track, and render everything in a scene, we also know where everything is, and all of that information is available to any sensor. This means you can model new kinds of hybrid sensors or sensors which provide higher level object information to your autonomous driving software. Those sensors can then be built as DLLs, shared, attached to ego vehicles, and loaded as plugins by a pre-built simulator binary, which means that other users who want to use your sensor do not need to modify or rebuild their own forked version of the simulator source code. Thanks to a collaboration with Velodyne, we have a new Lidar sensor plugin that simulates the specific scanning patterns of the Velodyne VLP16, VLP32C, and VLS128 Lidar sensors, and publishes that raw data over UDP for the best performance and compatibility. You can even visualize this Lidar data using Velodyne's own VeloView tool, which thinks it's actually receiving data from a real sensor. When LGSVL Simulator was first released as an open source simulator on GitHub, anything you wanted to extend or customize had to be changed directly in the simulator source code before rebuilding the entire project. Since then, we've created plugin APIs for many categories of extensions, including not only sensors like the Velodyne sensor plugin we just saw, but also for vehicle dynamics, NPC behaviors, and controllable objects that can be added to a simulation and controlled through the Python API. We have plugin support for external sensor bridges to further improve performance and to make it easy to support other sensor frameworks and proprietary AD stacks. Because we support FMI and FMU, co-simulation is possible with traditional automotive simulators such as CarSim, IPG CarMaker, MATLAB Simulink, and others. You can see examples of CarSim and CarMaker co-simulation here. We get a lot of questions about system requirements, so I'll talk about that next. LGSVL Simulator runs on Windows 10 64-bit or Linux, specifically Ubuntu 18.04, though some folks are moving to Ubuntu 20. There's no hard minimum for number of cores or clock speed, but you'll want a relatively powerful system like a typical desktop gaming or graphics workstation. A high-end gaming laptop can also work depending on the GPU. For best real-time performance, we recommend NVIDIA GTX or RTX graphics card with at least 8 GB of GPU memory. Some GPUs have 11 GB or more, which is even better. Older GPUs may have issues supporting HDRP or Vulkan if on Linux, and many have less than 8 GB of memory. GPU memory is really important when you want to simulate complex 3D environments, particularly if they contain a lot of unique textures, and especially if you're going to try to run the AD stack on the same machine as the simulator. In general, you'll have the best performance and best results if you run the AD stack on a separate machine, but it is possible to run everything on a single Linux machine. With separate machines, you can run the simulator on Windows where you may see better performance. Another thing that affects performance is the number of sensors you choose to enable, especially multiple cameras and lidars. If your ego vehicle needs several sensors, then you'll want to have a high-performance workstation and GPU dedicated to the simulator. Sometimes you may need more sensors than you can effectively render on a single machine, either a single vehicle with many sensors, or perhaps a simulation with multiple ego vehicles, each of which can have its own sensors. In this case, you may wish to configure multiple machines to run in a simulation cluster. With a cluster, different sensors will be assigned to render on different but synchronized simulator instances within the cluster, all of which will work together to generate in real time all of the sensor data needed for the simulation. Other simulators may resort to non-real-time simulation, but we wanted to be able to support hardware and software in the loop simulation, where you can literally take the AD computer out of a vehicle, connect it to LGSVL simulator, and generate all of the sensor data in real time, just as would happen in a real car. In order to do this, we came up with something we called distributed simulation. By running several instances of LGSVL simulator synchronized across a cluster of workstations and GPUs, we can assign sensors to render on specific instances within the cluster. You can see an example of that here, where two instances are fully synchronized with each other, and each one renders different sensors. Because we also support real-time simulations with multiple ego vehicles, each with their own sensor bridge to a separate AD stack, you can configure as many sensors as you need on each ego vehicle using distributed simulation. Now that you've heard about our sensors, let's talk about maps. We've built a road and map annotation editor into LGSVL Simulator, along with support for importing and exporting HD maps in a variety of formats, including Lanelet 2, OpenDrive, Autoware Vector, and Apollo. What does that mean for you? To start, it means that you can import an HD map in any of the supported formats, but HD maps don't generally contain enough information to render a 3D visual environment suitable for simulation. So you'll have some additional work to do to create a drivable mesh and create or add other visual objects into the scene. However, once you have created or imported a 3D environment for your simulation using your own assets from the Unity Asset Store, or exported from other tools, you can then annotate your environment, indicating lanes, intersections, traffic signs and signals, stop lines, pedestrian paths, junctions, crosswalks, parking spaces, speed bumps, and more. This information is all needed in the simulator to control the stoplights, as well as inform our NPCs, like our non-ego vehicles and pedestrians, where they can randomly drive or walk, since unless you specify otherwise using our API, they will generally obey traffic lights, traffic laws, and other rules of the road. Once you have an annotated environment in the simulator, you will not only enable simulation of the ego and NPCs within that environment, but you will also be able to generate and export a corresponding HD map, which is needed by your AD stack to navigate the ego vehicle within and around that environment. As I alluded to in the previous slide, creating a realistic 3D drivable mesh from scratch for your simulated environment is not a trivial task and typically requires the time and skills of a 3D artist. However, in order to simplify this process, we have created a new mesh generator tool in LGSVL Simulator, and I'm going to show you a demonstration of how that works. We've already downloaded a sample OpenDrive map from the web and created a new scene in Unity with our simulator project open. We first select and import the HD map into the scene using our HD map importer. We can then verify that the imported annotations are correct. Next, we select Build HD Map Mesh from the simulator menu to generate a road mesh from the imported annotations. We verify that the road matches the annotations and save the scene. We position the spawn info object. This is where the ego vehicle will be spawned in random traffic simulations. Next, we generate the nav mesh to enable pedestrians. We select the Mesh Renderers filter in the Objects tab and select all of the filtered objects in the scene hierarchy. We mark them as navigation static and define the type of surface. Then in the Bake tab, we click Bake to generate the nav mesh. We inspect the nav mesh to make sure there are no holes, and we save the scene. To build our new environment, we select Build from the simulator menu. We locate and select our new test map in the list and click Build. Once the environment is built, the map can then be used in simulations as well as with our visual scenario editor. Now that we have imported an annotated HD map and used our mesh generator tool to create a drivable mesh and built an environment, we can launch a simulation and observe NPCs randomly driving around within that environment. To summarize, if you have an HD map, which you probably do if you're doing any road testing, then you can easily create a drivable 3D environment for testing in LGSVL Simulator. The mesh generator is a new feature that will be available in our next public release. Of course, the point of autonomous simulation isn't just to watch NPCs drive around, but to test your own autonomous driving software. LGSVL Simulator includes out-of-the-box support for several open-source autonomous driving software and sensor bridge runtime frameworks. That means we support integration with AD stacks using our built-in support for ROS and ROS2, as well as CyberRT, and we provide everything you need to work with both Apollo from Baidu and Autoware.auto, as well as Autoware.ai. Here you can see examples of both Apollo and Autoware working with LGSVL Simulator, as the simulator provides the sensor information to the AD stacks, which they then use to control the ego vehicles as they drive down the road. If you'd like to set this up for yourself, please check out our detailed end-to-end tutorial videos for Apollo and Autoware at the link shown. We've talked about testing millions of miles, but how do you create millions of miles of test cases? It's certainly possible to script those tests using the extensive Python API that lets you control everything in a simulation, but it can be tedious to specify every detail of each individual test in Python. Fortunately, there are other ways to generate test scenarios. We can use a high-level scenario language like Scenic. Our pluggable test case runner includes support for running powerful abstract scenic scenarios that can randomize a variety of parameters for a test, including locations, environmental conditions, placement, and speed of other actors, and so on. We can perform resimulation from logged data, either from previous simulations or as captured from actual on-the-road testing. And we can use our new visual scenario editor to create and edit scenarios right inside the simulator. We're very proud of our new visual scenario editor, which was developed in Unity and is fully integrated with the LGSVL simulator. After launching the editor, you will see a top-down view of the currently selected environment. This one happens to be one of our photorealistic digital twin environments. We can drag or pan around the map and can zoom in and out as well. Because this is not just a 2D map view, but an interactive 3D view of our simulation environment, we can switch to alternate camera modes, such as a 45-degree view or a free camera mode, which gives us the ability to rotate the view. From the agent panel, we can choose an Ego agent vehicle. It will be downloaded if needed. We can drag an Ego agent vehicle and drop it onto the map. It will be snapped to the lane. We can then select and drag other NPCs onto the map, like the hatchback or school bus. We can also add a pedestrian agent. We can then disable snap in the editor options and can then freely adjust the position of the agent or rotate or delete the pedestrian or other agents. We can add a controllable object, in this case, an electric vehicle charging station. Next, we'll switch to the Edit Agent panel. We'll select the Ego vehicle and add a destination point for it. We can adjust the position of the destination point so the Ego will drive through the intersection. This destination would be sent to the AD stack, which will control the Ego vehicle. We can select a behavior for our school bus NPC, like waypoint or lane follow behavior. And we can adjust parameters such as the color of the NPC. We can also specify a maximum speed for the vehicle. We can then select the other NPC vehicle and add some waypoints so the NPC vehicle will also drive through the intersection. When we select a waypoint, we can set parameters for that waypoint, such as speed and wait time. And we can add triggers like a time to collision trigger. We can also add a waypoint for our pedestrian agent, Bob, so he will walk across the street. And finally, we can switch to the playback panel and play back our new scenario to test the agent behaviors. I'll run it one more time after this. The Ego vehicle doesn't move because in this case, we're working in the editor and we don't have the autonomous driving stack connected to it. I mentioned earlier that it's possible to run the AD stack on the same machine as the simulator, but that can be challenging, especially if you're trying to run Apollo, including perception and traffic light detection. Those modules consume a lot of GPU memory, which is also needed by the simulator. Still, not everyone has multiple machines available to give the AD stack a separate CPU and GPU from the simulator. Sometimes you just want to test the prediction, planning, routing, and control modules without worrying about the extra computational requirements to render camera and Lidar sensors or run the corresponding perception modules. For cases like this, we configure our 3D ground truth and traffic signal sensors to provide the same output as Apollo's perception and traffic light modules. As you can see here, Apollo stops for a red light, but there is no camera sensor or perception module running. When the light turns green, the signal sensor in the simulator tells Apollo the light has changed. and the ego vehicle continues driving. Note that Apollo can also recognize and display other vehicles in the right side Dream View window, thanks to the 3D ground truth sensor. You can see vehicles recognized behind the ego vehicle as it drives, and pulling up alongside of the ego vehicle at intersections, like this one, where the ego will once again stop for the red light and wait for the simulator to indicate that the light has changed. You've now seen our photorealistic scene generation and environment, our physical and virtual sensors, a variety of plugins, distributed simulation, and environment and scenario creation. I hope this information inspires you to download and try our LGSVL simulator. Before we wrap up, I'd like to share some links you may find helpful. First, you can find our website at lgsvlsimulator.com, including documentation, news about the latest releases, frequently asked questions, and more. You'll also find links to our simulator videos and hands-on tutorial videos for Apollo and Autoware on our YouTube and Bilibili channels. You can download a pre-built binary of LGSVL simulator or the full source code from the open source project on GitHub. And finally, you can email us at contact@lgsvlsimulator.com if you have any questions. Of course, specific technical or even general interest questions can always be posted to the issues page on our GitHub site. And if you search there first, you may find the answer is already there.